Good afternoon. Thank you for joining us for this webinar titled Solved: Finding Reliability Data for System Designs. My name is Richard Wisniewski, and I'm the Senior Reliability Engineer here at Quanterion Solutions. I'm joined by a Senior Engineer, my colleague, Chris Maxwell, who is my co-presenter for this webinar. I'd like to express my sincere appreciation to all of you for taking the time to join us today for this very relevant topic. First, I'd like to briefly introduce the company providing this webinar, Quanterion Solutions. Quanterion Solutions is a technical solutions provider headquartered in upstate New York with decades of involvement in the reliability engineering field. Quanterion Solutions provides customized training, consulting, and data analysis for reliability engineering, and in the past has operated the Reliability Information Analysis Center, also known as the RIAC. In today's webinar, we'll be covering reliability engineering data as it applies to system design. Now, before we begin, please note that attendee lines have been muted. If you have questions during the webinar, we ask you to submit them using the attendee chat box or the Q&A chat box. We will work to save the last 10 minutes or so to go over questions. Please also note that this webinar is being recorded. A link for the recording and slides will be available at the Quanterion Solutions website for later download. Now, with that, it is my pleasure to begin the webinar presentation. Now, during this webinar, we are going to be discussing the purposes of reliability predictions for system design, the problem with finding and accessing high-quality field data for predictions. We'll present a solution to that problem consisting of comprehensive data sets, along with providing an instruction in how to use and access those data sets. Now, traditionally in the past, reliability predictions have been based upon results of formal test programs. And it doesn't really take much in the way of common sense, okay, to understand the shortfalls with this particular type of approach. Testing typically can't be performed unless you build a prototype, and that's going to require a somewhat mature design. The purpose of doing a reliability prediction is to try and discover areas where you might have increased reliability risk, and try to determine whether or not it's feasible for you to meet a reliability requirement. And waiting until you've built a prototype is going to limit you in terms of your potential solutions, because the design is going to be solidified. And also, at that point in time, you've probably realized a good majority of your total life cycle cost. An alternative to this approach is to perform reliability predictions earlier in the development process using any one of a number of analysis-based techniques. This provides a way to track the reliability of the design as the design phase is progressing. This will help you to discover reliability risks early, so that you have the ability to design corrective actions to address, to either eliminate or to mitigate those risks. Hopefully you'll have more in the way of design alternatives at that point, because the design will still be fluid. Now, many systems are too complex to estimate their reliability as a standalone unit. Frequently we break these down into lower levels, okay, that are more easily handled. Okay, so we can take a system and we can break them down to LRUs, to subassemblies, to circuit boards, and all the way down to the component level. Okay, and by analyzing or assessing the reliability at these low levels, we can then use that information to build up the reliability assessment at the high system level. Now, reliability predictions are good for feasibility evaluation. Okay, if I'm starting out designing a piece of equipment and I have a requirement, is it feasible for me to meet that requirement? Okay, and reliability prediction will allow you to do that, or early on. And if it is feasible, fine. If it's not feasible, might be indicator that you might need to start building into redundancy or things of that nature into your design in order to be able to meet your requirements. Reliability predictions also are also good for analyzing or comparing competing designs. As you go through a design process, it's common, okay, to have a couple of different paths that you can go down. And, reliability may be a discriminator. And if it is, a prediction will provide a common basis for evaluating the reliability of each of the competing paths. Also provides you with a indicator of potential design problems or potential areas of higher risk. And then, of course, predictions are used as inputs to other tasks and analyses, such as FMEAs, fault trees, safety analyses, and maintainability analyses as well. Now, there are, of course, many misapplications of reliability predictions. And the first and foremost is this first bullet here, and as an absolute measure of field reliability. This is probably one of the most common misapplications that I come across, during my career, is people attempting to use a prediction as an absolute measure of field reliability, and also the third bullet, using the results of a reliability prediction as proof of reliability requirement compliance. Both of these are misapplications. Reliability predictions will never be an absolute measure of field reliability. The field reliability is going to be whatever is inherent in the design. And unfortunately, you won't be able to know that number unless you're able to keep good maintenance records and good field data records, and as a result of a good field support program after the systems have been working in the field. Without that information, you're probably not going to know what your true field reliability is. You'll be able to make estimates, but the one thing you can be assured of is it's never going to match your predicted number. Just several different reasons for this, both on the prediction side and on the field side. On the prediction side, incorrect and incomplete assumptions. Environments are often more complex than what gets modeled into a reliability prediction. Reliability predictions often account for maybe one or two of the stresses, hopefully the most appropriate stresses, on components, but certainly not all. Also, there's issue with unrealistic part quality assumptions, and and so on the prediction side. On the field side, just simply maintaining a good field data collection program is very difficult. Okay, you need to be able to account for all the failures that occur in field operation. You need to be able to account for all the field operating hours, during field operation. And if you have populations numbering into the hundreds and thousands and so on, the ability to collect that information is difficult. Okay, and it requires dedicated effort. That is, on the field side, an issue. Now, as far as reliability prediction methods are concerned, there's several broad categories, beginning with empirical models, physics-based models, comparison with field and test data on a similar product, stress strength methods, and also surrogate data. These are the methods we'll be talking about very briefly. And the first one being empirical models. This is an approach where you've taken field data on systems, on fielded systems, operating in a number of different environments with a number of different operating stresses, and you pretty much normalize those failure rates down to a standard set of standard environment and standard set of stress conditions, and then use those base failure rates in a mathematical model, to calculate the failure rate under different sets of operating conditions and under different environments. Examples of an empirical approach are like 217 plus, Mill Handbook 217, which is probably the most recognizable, Quanterion, all three of those, for electronic components. And then for mechanical components, NSWC 11 would be a representative sample of an empirical approach. Some pros and cons is with anything else. With empirical models, they can reflect, they reflect actual field failure rates because that's the source data. That's where the data came from in the first place, is from field data. The models tend to be relatively easy to use. System complexity is inherently accounted for, via component type, and the primary stresses that affect reliability are typically accounted for in an empirical model. On the other hand, they are difficult to keep up to date. The last time, for example, Mill Handbook 217 was updated was 1995. So that kind of gives you an indication that keeping models such as this current, is difficult. And of course, it's difficult to collect good quality field data as well, to develop the models. Those are probably the two biggest factors, affecting empirical approach. This slide here just shows the familiar bathtub curve, showing the three regions: the infant mortality region, the useful life region, and the wear out region. The infant mortality characterized by a high but decreasing failure rate, which is indicative of quality issues, manufacturing issues that have been built into the hardware inadvertently, and have not been discovered during the screening process before delivering the product to the customer. The useful life region, characterized by by a reasonably constant failure rate, is indicative of random type failures, or at least by failures due to a wide variety of causes. And then, of course, the wear out region, we're talking about an increasing failure rate due to reaching the life limit of a particular product, particular component, starting to reach the end of material stresses or material strengths, starting to be exceeded. The empirical models are pretty much trying to measure this distance between the horizontal axis and the bottom of this bathtub curve. That's the parameter that Mill Handbook 217 and Quanterion and 217 plus and so on try to measure. The physics of failure modeling, here they try to examine an item's main failure mechanisms and model those failure mechanisms, which of course would include the scientific and physical causes of failure, and also attempts to model the various factors that would affect the rate at which those failures occur. Okay, so this is made development of a mathematical model as well. And this is, example of, a listing of, some failure mechanisms that could be covered by physics of failure models. Each failure mechanism would have a model associated with it. And of course, there would be acceleration constants and acceleration factors that would be applicable to those models, which would, try and predict the rate at which those failures would occur. There's, again, pros and cons with this methodology as well. It does predict end of life. It does model specific applied loads, and it explicitly models loads variables that cause failure. And because, and we're also examining failure mechanisms. Okay, so we're looking at, the reasons why, components fail. On the other hand, the methodology tends to ignore defects. It does not predict failure rate during useful life. It does predict end of life, which is not the same. It's not the same parameter. The models do tend to be very complex. Detailed input data is necessary in order to make use of the models, and also detailed knowledge of material properties of the components involved are also required. Looking back at this bathtub curve, this just shows the parameter that tends to be predicted by physics-based models, which is basically end of life. Another methodology for performing predictions, statistical analysis of failure data. This is basically a method that would be used if you have a legacy design and that was used in a similar application. Okay. So if you have a system that's similar to something that you've designed and fielded previously, you can use that information if you've kept good, if you have good field data. So operating time, failures, et cetera, for your legacy design. You can then take that information. Perhaps you've got a new design now that you've maybe refreshed some components in there, to update the technology. Perhaps you've added some features to the design. Perhaps you've deleted some other things that are no longer necessary. But large parts of the legacy design are still in place in your new design. So you can address those things. You can address complexity with a complexity factor, and that can be based upon differences in part count, for example, or differences in the number of active circuits or the number of connectors. However you want to define complexity. You can also make adjustments to that legacy failure rate based upon the environmental differences, temperature differences, and so on. Well, the stress strength method, this is an approach, when you might have a component, for example, that's being exposed to a stress at a certain level, and it's rated, it has a rating or a strength, that at a different level. And you wanted to determine whether or not, this component is likely to fail, during the service life of your equipment. Now, as an example here, if we suppose that we have a stress on a component, for example, 2,500 PSI, and the strength or resistance to failure is 4,000 PSI, by looking at those numbers, you might conclude that, I'm okay. Okay, I've got adequate margin. and I shouldn't expect this component to fail for this particular reason during the life of my equipment. And if you could view these two parameters as point estimates, then that would certainly be true. But in reality, there is variability that exists around both of these parameters. And so, for example, if I try and now take into consideration that there might be a standard deviation among, about each one of these parameters, I'll see that I actually have distributions on the strength and distributions on the stress. And this region where these two curves overlap represents areas where you could have in your population individual components that are on the high end of the stress curve. So they might be experiencing higher than normal stress, but they themselves are on the low end of the strength curve. So they're actually, their resistance to that stress is actually lower than normal. And if you have an area where the actual stress exceeds the strength, then you will have component failure. And then by analyzing these, statistically, depending upon what the statistical distributions are, you can calculate the probability of failure. And then the final method that we'll discuss is the surrogate data. This is simply, a method where you use recorded field failure data from similar components that that have been aggregated. The same general design, same general size, similar conditions, for example, and use that aggregated failure rate information in your current design. Okay, and examples of these surrogate data sources are NPRD, PRD, and FMD, which we will be discussing. So what just brings us to how do you access surrogate data? Okay, you might have a design that has hundreds, maybe thousands of components. Okay, some of them you can analyze using empirical models, some of them you can analyze using physics-based models or what have you. But there may be a subset of those that you're not going to have empirical model. Perhaps performing physical failure analysis is not going to be feasible. So you need to resort to surrogate data to try and estimate the reliability of those components. And if you have hundreds of components, in your system that you need to do this for, where do you get the data to do that? Okay, vendors might have some information. If they do, it's going to probably be based upon test data, which might be under controlled conditions and not necessarily integrated with other components. And that's if you're lucky. Okay, in all likelihood, quite frequently, vendors don't provide, failure, reliability information or failure rate information for their components. So it would be good if you had a, single reference where you could go and you could get this information. And, Quanterion, over the years has developed three main databases to address this type of problem. Okay, the first one being the non-electronic parts reliability data for mechanical components, the electronic parts reliability data, or EPRD, for electronic components, and then our failure mode and mechanism distribution database, which contains information on component failure modes. The most current version of our NPRD data set is NPRD 2023. It was just released in April. This is a compendium of component failure rates for mechanical and electromechanical parts and assemblies. Represents a cumulative compilation of data collected between 1970 and 2022. Covers roughly about 28,000 component types, and it contains about 1.5 million data records. These are some example categories that are covered in NPRD 2023. Like I say, there's about 28,000 unique types, part types. So this is a real small example set. The full set of part descriptors that are available in 2023 can be found in this PDF. And a link to the PDF has been provided here in the slides. Where you can see that full list of part descriptors. Okay. This is an example of NPRD data, example page of NPRD data. So you can see it contains the part descriptors. It contains the quality level, whether it was a commercial component, military grade component, or whether it was unknown. It contains the environment that the data came from. And most of these environments are similar in description to the environments found in Mill Handbook 217. So you have your ground mobile, your space flight, your airborne and uninhabited fighter, and your airborne uninhabited cargo, and things of that nature. Also contains a data source that, where the data came from. Contains the failure rates in terms of failures per million hours. Cycles or miles, depending upon the source. Contains the total number of failures that were reported by that reference, that data source, as well as the total number of operating units during that, reported by that source. EPRD contains similar information for electronic parts and components. This is EPRD 2014 is the most current version, although an update is expected sometime probably during the fourth quarter of this year. Again, this is for electronic components. And FMD provides failure mode and mechanism distribution data for a wide variety of electronic and mechanical components. This one contains about 900, just under 1 million data records, and it provides information on failure modes, failure mechanisms, and also the percentage of the time that particular component types fail in each mode and by each mechanism. And again, this is also based upon field data. So with this, I'd like to turn this over to my colleague, Chris Maxwell, to give you a demonstration on how to access this information.
Okay, so thanks, Rich. So what I'm primarily going to talk about today is ROADS, which is the online accessible database, the Reliability Online Automated Data Book System, ROADS, which contains all of the data sources that we just talked about. So a subscription to ROADS provides, as it says, an online automated system of searching and referencing NPRD, EPRD, and the FMD. So what I'm going to do is I'm going to try to present this from a novice's perspective. And full disclosure, I'm somewhat of a novice on ROADS myself. And Rich is the expert on the data behind ROADS, so he may interject at times to elaborate on some of my descriptions. But I feel like this will help novice users, and we can sort of explore together. Hopefully I won't be moving so fast that you're wondering what I'm doing. So what we're going to do is we're going to navigate your login in your account. We're going to manage what data sources are available on your account, where to find background information to facilitate search and interpretation. And essentially that's what I'm calling how to set up your lifelines. So if you're a novice, when you first get in, set up some lifelines and your experience will be much better. Examples of searches and search methods, which may get interesting, but we do have some canned ones to show you, and then we'll try to answer some questions that come in, and we'll see how well we can navigate based on some random inputs. So to that effect, if you look under my account, which I'm going to show you some slides right now to sort of give you a map of where I'm going to go. But then I'm going to show these slides, and then we're going to get right into roads, and then we're going to go there. So this is the lay of the land. Your data sources are set up under, you go to your login circle here, you go to my account, and you can set up which data sources are available. Subscriptions include all three of these data sources. The main thing that you might want to do is adjust which vintage data you're going to use. It's recommended that you use the most current data, because the current data, say NPRD 2023, includes 2016. It doesn't truncate 2016 and then add. So you're going to get all of 2016 and 2023. You're going to get all of 2011 and 2023. The only reason you might want to exclude the newest version would be if you've already done a reliability prediction or a data source lookup, and it was based on 2016 or 2011, and you've done this for numerous items, and you want to be consistent with how you source your surrogate data so that you can perform relative comparisons from one system to another, which, given the statistical nature of reliability prediction, that's a non-trivial concern. Sometimes you want to go back to the old data just so that you're consistent. This data source text is available. This, to me, is important in setting up your lifelines. The introduction information from all of the printed books that we have made for the various data sources, which NPRD 2023 is not available in print yet, but it will be soon. But if you're familiar with the books, you can see that text from within roads. So if you like to navigate with text, you can do that while you have roads up. So the list of part descriptors is also available in text, which can help you find search terms if you're floating a little bit, or sort of wrapped around the axle trying to find a search term. My personal comment here is I feel it's the best of both worlds. The user can use the tools within roads, and then in other tabs that can be up simultaneously, you can go back and look at your lifelines to help during your search. Now, the main search methods, we're going to explore these. This is just a reference slide. When you get into roads, it's nice to know how these different search methods work. Your primary index search means that it's a primary term that you're searching on, and your search results can be anywhere in the description. Okay, so you're searching on that word that you're searching on is more important than the description. And so you're going to get all results that have that word at the beginning, in the middle, at the end. It doesn't matter. If you use a primary index, you're going to get every result that has that word in it or term. Part category, if you want to search by what would be at the beginning of the part description, which is common in a lot of bills of material, potatoes, mashed, right? If you're ordering lunch, according to most bills of material, it's going to be potatoes, mashed, not mashed potatoes. So you would search under potato, not mashed. Part description, search results will match entire search term. If you want mashed potatoes, you're going to have to say mashed potatoes, and you're going to get only mashed potatoes in your search. I know it's lunch and we're possibly all getting hungry, so I'm going to end with the food analogies. So within roads, I've already logged in. Just for expediency, but logging in is relatively easy. And we can help you with that process if you're a user of roads. But so let's talk about the first topic, which is exploring your login, right? I look at my account and it welcomes me, which is always nice. I feel welcome. But so here's my data book configuration. Right now I'm configured with the most modern version of 2020 NPRD, the only version of EPRD, which we've mentioned there's a new version of EPRD being published soon, and the most recent version of FMD. This is my subscriptions, whether they're active, whether they expire, and my password is hidden, thankfully. So let's set up the lifelines. Lifelines are in text. So I'm going to open the NPRD introduction, okay? Notice it opens in another tab, so it's going to be open even while I can search and I can bounce back and forth between the tabs. To me, I like to go to page 19. You can look through the entire introduction. It's all, the whole PDF is there. Page 19 gets you to, this is the field descriptions when you look at the data. For instance, the column descriptions of that example page that Rich just showed you a few minutes ago. Table of application environments. If you're wondering if this code matches the environment that your product is going to be used in, this is the best place to look that up. A little treatise on how we handle merging data and collect, how we statistically analyze the data. A little discussion about the impending failure assumption, which answers the mystery of when you're looking at the data, you see a failure rate, even though there are 0 failures listed. Well, we assume that 1 failure happened under all the accumulated hours, and then we say the failure rate will be less than the failure rate if 1 failure occurred. Okay, so the impending failure assumption is explained here. So that's the first lifeline. Next lifeline that I would set up, especially if I'm using NPRD, is down here. I would go to the part category descriptors, because just based on my little explanation about how words and part categories and part descriptions sometimes start with different words than you think they would start with. Sometimes it's nice to have this, and sometimes a Control F and a text search here can get you can sort of get you oriented and give you some inspiration as to what to search on. Another thing that I would usually open as a lifeline would be the, and actually I hit the wrong one. Going too fast, right? I said I wasn't going to go too fast, and I did. FMD 16. The FMD, as in the fractions of failure modes in those distributions, are available for every part that you search, okay? And so that data is available to you in roads with a click. And once you see that data, it would be nice to be able to essentially interpret that. In the section here that I like to refer to is page 17, data interpretation, and that will help you to get to essentially know what's going on when you read the data, okay? Specifically, if you want to know the difference between the normal distribution and the failed distribution. So those are the lifelines. One other lifeline that if you are searching on NSNs and national stock numbers and things, if you open yourself another tab and if you just type in I'm looking at, I have to type it in. I didn't copy it. Land and marine, maritime, I should say. apps.dla. And I have caps lock on, which I'm going to turn off. I'm not yelling at you. Okay. Yes, it says warning batter, but you know, galvanize your nerves. It's going to be okay. It's just saying, you know, in here, this you can do parts searches for if you have an NSN. You can put that search in here. And this is handy if you search an NSN and you can't find that NSN in roads, you can go out there and find a description. Okay, let's get a little bit into roads. Okay, so the first part that I'm going to search is, I have a little bit of a canned search here, and we're going to search a brake assembly. Okay, now if I want to search a brake assembly, I already know what that description is, but I'm just going to show you how it works in the tool here. If I type brake here in primary search, a selection list will come up, and you're going to get anything with the word brake in it, and you might also get some close relatives of that, if you will. If I go over here and search brake, brake's going to be the first word, so brake assembly is a choice there. Okay, if I come over here and search for a brake assembly, by the time that I type the word brake, I do get these choices, but they're not going to narrow down too much until I say assembly. Okay, and then I get like disc brake assembly, things like that. I'm going to go back here to part category, and I'm going to select brake assembly from there. Now, once you've filled this in, you have to do search with qualifiers to get your results. Okay. First thing I want to talk about, now that we have some results up here, we chose this example to let you sort of get oriented how the data is presented. One of the main things, which you can see if you go up to the introduction in 2023, it's going to talk about how failure rates are presented. They're normally presented in failures per million hours, but if you see a C, that's failure per million cycles, you might see an M for failure per million miles. And there are a couple of other spurious failure rate quantification factors that could be involved. But you know, C means cycles, M means miles, which is important, especially for ground mobile stuff. If you look up a connector in the EPRD, you might see its failure rate in million miles. If you look up that same electrical connector in NPRD, or sorry, you would see that failure rate in failures per million hours in EPRD. If you look it up in, if you look it up in EPRD, you will see failures per million hours. If you look it up in NPRD and you look under ground mobile, you may find that electrical connector is used in a car or a vehicle and the failure rate will be presented in miles. Thank you for bearing with my little bit of confusion there. But this shows how data is rolled up. Okay, brake assembly, military quality, airborne attack. Okay, yep, has a failure rate less than 1.49 failures per million hours because 0 failed, and essentially there was 1.49 million hours of data collected without any failures. So if one had failed, this is what you would get. There's data among the brake assemblies. There's data that's a mixture of failures per million hours, failures per million cycles. Lots of times, if you're looking for applicability of data, you would move up here to a roll-up, some type of roll-up. This is going to be a roll-up of all of the data sets that were done in cycles. Okay. This is going to be a roll-up of all the data sets that were done in failures per million hours. And then break assembly summary will also include different descriptions of break assembly, if there are any, which there aren't in this case. Everything that's brought up is just break assembly. But the break assembly summary might include, say, break assembly, comma, landing gear, something like that. Failure rate details. Failure rate details are essentially referenced and indexed by these source numbers that we're looking at. So you would have to, if you wanted to explore one of these sources, remember this number, go to your failure rate details, and the source will give you these details. Okay, this is sort of a summary. 5 failures, 357 parts in the population. If you click over here, you can get even more details, possibly even the part number, manufacturer, and sometimes within that data set, this 22.1.10.19, there may have been one part that was, that met this break single disk category, and other parts may have met that too. Okay. So let's go back to the search. Then I want to explore failure modes. So if you bring up failure modes, this is the failure modes that's relevant to the part description that you just searched. Okay, the normal distribution and the failed distribution. And the main difference here is the normal distribution ignores unknown failures. It ignores others. It also ignores induced failures. For instance, failures that are induced by excessive stresses on the component. Your failed distribution includes all of those. And so depending on how you want to look at the fraction of failure modes within the overall failure rate, you can select from either of these. So for instance, if you had brakes, if you were looking to, if you had done an FMEA and you had determined that worn brakes was a failure mode for this type of failure, and loose brakes was the failure mode for another failure in your FMEA, you would say the probability of the worn failure rate, assuming you had 1 failure per million hours, would be that failure rate multiplied by your choice of distribution, whether you want to use normal or failure distribution, failed distribution. The probability of loose brakes as a failure mode would be the overall failure rate, which we had just looked up, multiplied by the appropriate distribution. At this point, I have used up my time allotted for the demonstration. So I'm going to turn it to Rich for a couple of minutes to just do a few slides, to pay the bills, and then we'll get to your questions. Thank you.
Okay, thank you for joining us today. In a moment, we're going to answer questions that you've asked during the webinar. And then, during this time, you can also continue posting questions to the chat and to the Q&A. As we mentioned previously, Quanterion Solutions provides training that covers some of the topics that we briefly discussed today. And in fact, we do have an upcoming open training available for registration. That's going to occur September 12th through 14 in Albuquerque, New Mexico. 2 courses being offered. One is quantitative reliability analysis that I will be teaching. And then another one is Weibull analysis that we'll be teaching by Fulton Findings. You can sign up to those for either one of those today. And then also, as I mentioned briefly, that Quanterion offers consulting as well. And if you're interested in learning more about our reliability engineering solutions, feel free to reach out directly using the contact information in the chat. You can also sign up for our reliability engineering emails and they provide a wealth of resources for you as well. Now, at this time, we would like to answer your questions. And as mentioned at the beginning, the slides and recording of the presentation will be made available for download.
Okay.
Okay, Rich, we have some questions from the audience. The first one is,
I'm looking at some of the questions here in the meeting chat.
Yeah. So how
Are the
does
REL engineering
surrogate
and Vital
data?
presentations available virtually? I don't believe so.
No,
Right.
no, they would not be.
Jorge Velasco, hold on, I need to go back. Can the failure rates obtained from the NPRD, EPRD be adjusted to the environment and temperature conditions of my system? Not directly. You would have to look at a failure mode / mechanism individually, and then you would have to see if you know something about the physics of that failure. And you would have to maybe calculate an adjustment. It's almost as if you're building your own empirical model. There are caveats there. I have a question about NPRD standard. If the reliability analysis is required for mechanical equipment, the NPRD standard can directly be used for a reference value. But how reliable is this method itself? Because this catalog value does not include anything about my design. Do you think? Well, that's the downfall of surrogate data itself. Surrogate data represents average failure rates over the good thing about NPRD is it's broad coverage. The bad thing about NPRD is it's broad coverage, right? So the good thing is you can get a failure rate, you can get a ballpark, but by looking up similar parts in similar environments, but if you have a new part that, if you can think of any reason that it doesn't meet, say, the construction or usage environments, you may have to look at a different type of model than just surrogate data. Although surrogate data can give you a ballpark of what you would want to expect out of your new design. Any cons for using NPRD / EPRD databases? We covered them in slide 24 through 26. So there are pros and cons. Is SSI typically done for electronic components? My canned answer there is stress strain interference analysis for electronic components is often handled by derating, where you select a component by a rated value, and then you make sure that the applied stress is a certain percentage of that and not over. For instance, most people only use, say, tantalum capacitors at 50% of their rating, okay? The other, right, and Rich and some other support people here wanted me to make sure I reiterated. It's mentioned earlier, predictions should not be used as an absolute predictor of field reliability, right? They're relative. So the most applicable use of any empirical model or surrogate data is if you've used it for previous systems and then you use it again during the design of a new system, and then you can get a feel for your relative difference in reliability. I want to go back to the SSI question. For electronic components, stress strain interference is handled by derating. Another way that stress strain interference is handled is through worst case analysis. And you can look up references on worst case analysis. Under worst case analysis, you essentially look at the partial derivative of how a environmental effect affects the tolerance of your components or their ability to withstand stress. And then you use either the extreme value method or root sum of the squares method or a Monte Carlo method to accomplish an SSI analysis for an electronics component. Let's see. Oh, this is a good one for Rich. For Prism, the predecessor to 217 Plus, there were two papers presented at RAMS that compared their field data versus predicted from Prism. Are you aware of any published papers comparing fielded data versus 217 Plus predictions?
Not off the top of my head, no.
Right. And that leans into usually when we do 217 Plus predictions for customers, or when we do them ourselves, they are most applicable if 217 Plus was used for also for comparative systems, so that you get that good relative feel for reliability. The absolute feel would be very it's very tough to get an absolute feel from any type of reliability prediction method. For instance, if you look in our handbook of 217 Plus, which is the description of the models behind 217 Plus, there are some examples that use a few different reliability prediction methods on the same systems, and you get answers that vary by as much as tenfold. So picking and choosing one method or another, or mixing methods within a design, can be very problematic. Failure rates given in failures per mile is a conversion to rest of the world units a direct multiplication factor. Failures per 1.6 for kilometers.
I think that's going to be dependent upon your application.
Right. First guess is probably, but dependent on application, yeah. For NPR data, for total failures are 0. Oh, we already mentioned that. Essentially, one failure per all of the time within that data set, and then the failure rate is less than that. I once did a prediction for a version of the BlackBerry phone and managed to get within 10% of actual field failure rates using 217 Plus. When you've completed that, you should have gone down to the store and bought a lottery ticket. I'm glad that worked out, but that's good, but we can't guarantee that type of accuracy with every calculation. I am not very confident in field data. There is great lack of precise determination. Yes, this is true. So again, field data is used to get relative comparisons, ballpark figures, good first iterations to inform design choices early. In the end, you need to build a complete case of due diligence to back up your reliability prediction. For instance, most of the times when we do a reliability prediction for a customer, we'll do a reliability prediction and a derating and possibly a worst case analysis and an FMEA. All of those, and a reliability analysis or a reliability block diagram. All of those methods are, they support each other. So we would not recommend just doing a reliability analysis or reliability prediction based on surrogate data or even empirical models, and then just saying this is my absolute answer. 1258. I'm searching for some other questions that we can hit upon.
I think there was a question here about it, asking if it's possible to have access to each module separately. From a subscription standpoint, no. Subscription would contain access to all three databases, NPRD, EPRD, and FMD. While you're logged into Rhodes, however, it is possible to turn off
and I'm showing that right here.
Any one of those databases.
And that might matter, for instance, in the case where I was talking about looking at connectors. You'll find connectors in NPRD and EPRD. If you're in a, say, vehicle, you might want to look in NPRD alone and turn off EPRD. We are now 20 seconds out, so I'm going to go back to the slideshow.
We're about end of time here. So again, I'd like to thank you again for your time. We look forward to future interactions, and always appreciate feedback. And if you have any questions, if there's a result of this, you can always send your questions to Q Info.